all radical reactions tend to follow certain common pathways. So radical reactions, let's just entitle this. Turns out radical reactions typically occur in 3 steps. Number 1, you have the initiation step. In the initiation step, we are going to make radicals. There will be a net increase in the number of radicals in the reaction. So if we look at this, in a typical reaction, we'll have some molecule, and I'll just write XY, and we treat this with some form of energy. It could be heat. It could be light, which is denoted as h nu. That's the Greek character nu, h nu, and that's a light, a photon. It's a form of energy. And what happens is, through the action of heat or through the action of light, we break this bond in what they call a homolytic fashion. It's a homolytic bond cleavage, and we form 2 new radicals. So this process required the input of energy. And so our reaction coordinate, this is what this process would look like. We started with XY, and we end up with X radical and Y radical. So this is the initiation. Typically, you don't have radicals floating around in a reaction. Something has to form the radicals, and that is the initiation step. So step 2 is the propagation stage. You always have to look up how to spell propagation. And this is where the net reaction occurs. Okay, I think it's a little confusing, but the net reaction occurs, and there's no change in radicals, or no change in the number of radicals. Okay, what does this look like? Let's say the first step of our reaction involves some radical which formed, and it had to form in the initiation step, and it reacts with B, and we form product C, plus we get another radical out the other side. That's almost always the case. You put in a radical, you get a radical back out. Note that there is no change in the number of radicals in that step. And then radical D that we just formed reacts with something else. Let's say reagent E, and that forms compound F, plus reforms radical A. Okay, 2 steps. This looks like alphabet soup. What are we doing? So, if we think of this as a mathematical equation, let's add up all the things on the left and add up all the things on the right. So as it turns out, the A radical appears on both sides. So in net, we made an A and we lost an A. No change. D appears on both sides, so we'll just get rid of the D's. And now we see what falls out is the net overall process of these 2 steps is B plus E forms C plus F. This is our net reaction. And in our net reaction, our radicals don't appear in the net reaction. That's an interesting quality about radical reaction. So you need the radicals to make the reaction go, but they don't appear in the net reaction equation. Okay, so how does this all end? Well, it ends with the termination step, or termination stage. Now, in termination is the opposite of initiation. We're not going to make radicals, we're going to net destroy radicals. The concentration of radicals will go down as a result of the termination steps. So, termination is when any radical reacts with any other radical and forms some kind of product. So the opposite of the initiation step would be X plus Y as radicals, forming some molecule XY. If we looked at our propagation step, we have 2 radicals. We have the A radical and the D radical. And what would happen if those 2, by chance, bumped into each other? You'd form this product, you'd destroy radicals. That would be a termination step. In general, the concentration of radicals is extremely low because these are really reactive species, so they have a low concentration. Since their concentration is so low, the probability of them encountering one another is also extremely low. But it does happen, and it does result in a termination. So these are the 3 stages of radical reactions, and we'll try to remind ourselves of these 3 stages as we learn specific radical reactions, such as the halogenation of alkanes.